Okay, any questions from last lecture? If not, let me just recap briefly what we did in the last lecture. The main focus was on curvilinear coordinates. So we introduced the transformation from a rectilinear Cartesian frame to a general curvilinear frame. And given that transformation, that is unique both ways. You can go from Cartesian to curvilinear or curvilinear to Cartesian. We saw that keeping the point the same, we get the transformation equation. Keeping the distances the same, we get this metric tensor. And we saw an example with the cylindrical coordinates, how to calculate that metric coefficient. And I will make that as part of your next assignment. That mechanism is important to understand so that you can expand an equation of motion in any coordinate system. Today our focus is going to be mostly on development of the equations of motion. And we saw that if the metric tensor is diagonal, then it is orthogonal, the coordinate system. The curvilinear system is orthogonal. What it means is that tangent to the three curves at any point of intersection are perpendicular to each other, even though the curves are curved. Then you have these metric coefficients, which are the diagonal elements of that metric tensor. Once you calculate those metric coefficients, then expansion of these operators, the gradient, the divergence, the curve, etc., can be made in any coordinate system as long as we have those H1, H2, and H3, because there are standard recipes, formula for plugging in those metric coefficients and doing the expansion. Then we introduce this idea of an Eulerian and Lagrangian viewpoint. Lagrangian viewpoint is following the motion of a tagged material. Eulerian viewpoint is from a fixed laboratory frame. And in fluid mechanics, Eulerian frame is the most commonly used and most convenient one. But they are related. Obviously, it's the same phenomena that we're studying, so it should not depend on who studies it in what reference frame. So there is a relationship, a transformation, and that is given by this derivative, something called a total derivative or substantial derivative, which is related to the Eulerian derivative and what I call the advection speed or the convection speed. And we saw examples of a skydiver and other examples that relate the information from one reference frame to another frame. Towards the end of the last lecture, we actually ended up developing this continuity equation, mass balance equation, by taking an arbitrary material volume, Vm, and because it is a material volume, nothing can come in, nothing can go out. So the rate of change of mass inside that material volume is zero. That's what mass conservation tells us. And so we then used some mathematical tricks, which we are going to use again today. One is the Reynolds transport theorem, which allows us to translate from the derivative in a Lagrangian frame to an Eulerian frame. So applying that and applying the Gauss divergence theorem, which allows us to go from a volume integral to a surface integral. These are identities, vector identities, applicable for any quantity, any function. Alpha, for example, can be a scalar vector or a tensor. It could be concentration, temperature, density, velocity, etc. So we're going to use these two relations again today, but we're going to apply it to the momentum balance equation. So it's going to be a fairly strenuous exercise today because a lot of equations on the board. Okay. The first thing I want to do today in continuing to develop the momentum equation is develop something called the special form of the transport theorem. The transport theorem, if you recall from the previous page, is the one that allows you to relate the Lagrangian derivative of an integral quantity to the integral of the Eulerian derivatives, okay, and the surface and the volume. So this is valid for any general alpha. But what I'm going to do now is apply it to a very special case called the special form of the transport theorem by taking the general one. So this is the kind of thing that you have done in your assignment. When I give you the ED rule, for example, with two cross products, how to apply that and for a specific case when some index repeats, for example. So here I'm going to say that I'm going to let alpha is equal to rho g. So wherever alpha was there, I'm replacing it by rho g from the previous equation. Wherever there was alpha, I replace it by rho g. Okay? And then I apply to the right hand side, to this part of the equation. It's going to be, I hope it's not as difficult for you to follow on the board. I've written down all these equations because it takes a lot of time to develop it on the board, and my handwriting is also pretty bad. But I hope you can follow it. I will try to highlight it with colors and stuff. If something is not clear, please do stop me and ask me to explain. Okay. So what we are doing first is take this expression and apply chain rule on that. So d dt of rho g, and that's what this is, expansion of that by chain rule, which is rho times dg dt plus g times d rho dt. Okay, so is that clear? So that's the first part. The second part, I'm using, okay, let me ask you to get you involved in thinking. What am I using there? In going from this to this. Can you guys see in the back? Not maybe I'll come a little closer. So I've converted a surface integral to a volume integral using Gauss divergence theorem. Okay. When I apply the Gauss divergence theorem, it's basically on the surface, whatever is v dot n becomes the gradient dot on that quantity. Which one? Yes. Thank you. That's a volume integral. I cut and paste. That's very good. That should be v. From surface integral to the volume integral. Okay. So del dot of rho gv integrated over the volume. Now both the terms are as volume integrals. Okay. If you notice here, this is a volume integral and that's a volume integral. So I can combine them, and I guess before that I did one more thing, which is to take this expression. What did I do there? I applied the chain rule, but I applied the chain rule on this quantity g. Okay, so I have a product of del dot rho gv. Okay, so I can actually expand each one of them applying chain rule. If you have doubts in that, please ask me, and you should be able to you should feel comfortable in going to index notation, expanding it, and coming back. Here I'm simply writing this as I'm taking g out first. So g, then I have del dot rho v, plus I'm keeping g inside but taking rho v outside. Okay, so rho v dot del g. What you should pay attention to here is, where does the dot appear? By inspection, that should become kind of obvious to you, because here rho is a scalar, g is a scalar, but v is a vector. So I have del dot v, which makes sense. That's a dot product between two vectors. But rho and g are scalars, but they are scalar functions within that parenthesis. So the del operator, the delta operator operates on all three quantities in here. Okay, but when I choose to combine it as g and rho v and expand it, I get this one. Any questions on that? Do you see what's happening there? It's basically chain rule. If it's not clear, we can go and show that using index notation, how that would happen, and then come back to the Gibbs notation. Any questions on that?
Are all of those DAs supposed to be DB?
Yeah, I did make it. This should be V. Thank you. I will correct this and upload a corrected version on the web page. Okay. So that means we are now okay with this splitting of that term into two terms, and then I'm going to combine the terms that have g in them. For example, let me try to use a different color. Here I have g, and here I have g. So I've combined those two terms, g times d rho dt plus g multiplied by del dot rho v. Combine these two terms, and let me use the blue to combine the one with the rho, and with the rho here. Okay. Okay, so rho times dg dt plus rho v dot tau g. So I take the rho out. Okay, now I have a question for you from previous lecture. Do you recognize this term? That is the continuity equation that we derived in the last class. If you don't recognize it, you can just go back and you can see here d rho dt plus del dot rho v. Okay. I'm not going to ask you to remember any of these. So in an exam, I'll give you a formula sheet, or we can even have it as an open book exam if you all agree that Bird-Stewart Lightfoot is the one that you're going to have. Okay, so you can open it up. You don't have to remember anything, but you should be able to go from step A to step B in a logical fashion. Okay, so this by definition is equal to 0 because that is the continuity equation. So what we are left with then is rho times this entire term, which I can write in a compact form as the substantial derivative, the total derivative. So what has happened is finally I have this term equals this term. That is the equation. That is called the special form of the transport equation, where I have d dt of the integral of rho g dv is equal to the integral of rho times dg dt dv. So it allows me to switch the derivative and the integral operation for the very specific case. So this is applicable for fluid mechanics because we have used the continuity equation, the mass balance equation. Whereas the previous form of the Reynolds transport theorem is general for any vector scalar quantities. So we will use this later on because we need this tool in developing the momentum equation. That's why I briefly covered this. So there are a lot of equation steps there. I have laid out the steps in fairly detailed manner. So please go through that, and if there are questions, please do come and ask me. Okay. So we are now ready to develop the equations of motion and energy. Those are our goals for today. I'm going to develop the Newton's law of motion for fluids, the energy balance equation for fluids. So the first step is called the stress equation of motion. Okay. So once again, my approach is going to be take an arbitrary material volume. By material volume, I define that there is nothing coming in or going out. It's a volume with the same material for all the time. Okay, and the expression of Newton's law conceptually would be like this: the rate of change of momentum, linear momentum, is equal to some of the external forces. Okay, so if I give you that material volume and I say here is a point and that point has a velocity v and a density rho, what is the momentum? What is momentum? Momentum is mass times velocity, but density times velocity would be momentum per unit volume of the fluid. So you will find that the entire equation is based on momentum per volume, forces per unit volume, like that. Okay, so this rho v is the momentum per unit volume, but we are multiplying it by the volume dv. Okay, so that gives you at a point, a differential element, what is the total momentum. You have to integrate that over the entire volume, material volume, to find the total momentum of that material volume. And then rate of change, ddt. It is a capital ddt, meaning it is the material derivative following that particular material volume. Okay, so in the previous case, such a derivative for mass was 0 because mass could not enter or leave that material volume. In this case, the rate of change of momentum is going to be influenced by what forces act on that material volume. We're going to consider two types of forces. One is called the volume force that acts over the entire volume. These are long-range forces. Gravity is an example of that. In fact, we're going to include only gravity in there. Okay, so gravity, mass times g is the gravitational force. So mass times rho would be gravitational force per unit volume multiplied by the dv and integrate over that. So this actually allows for the fluid properties to change from point to point inside because we are going to do the integration. Okay, so you could have a heterogeneous material with varying densities. We will still be able to get the total force due to gravity that is acting externally on that body. Okay, plus this is why we prepared ourselves to be able to include these forces. The next term is the surface force, the force that acts on the surface with a normal n. And we knew already how to calculate such forces as simply n dotted on the stress tensor. So T is called the total tensor, okay, the stress tensor, and n dotted on T gives you the direction of the force acting on the surface. That is at an elemental surface. Now you carry out the integration over the entire surface, and that gives you the total surface force. There could be other forces that we could consider. Can you think of other forces that would move the fluid? Shear is included in this total stress. Okay, that stress has two components. One is the pressure, which is normal component. The other one is the shear. So T actually has both of them in it, and we will decompose that later on. But the one that we have neglected would be electromagnetic forces. For example, if I have charged species, ions, if I take sodium chloride and dissolve it in water, I have sodium ion and chloride ion. If I apply a potential to that, the ions will migrate. So that can make the flow move from one point to another point. Those are not included in this development yet. Later on, maybe in another course, we will look at electrokinetic flows that are driven by electrical charges. But for now, it's basically these two forces we're going to look at. This is called a surface force, forces that acts on a surface, short range forces, okay, and then the volume force. That is the statement in mathematical language, from conceptual to a symbolic language. What are the forces and what is the statement of Newton's law? That states the conservation of linear momentum. Rate of change of momentum equals sum of the external forces. We have considered two forces. Now what we are going to do is, that's a simple statement. Okay, so we are going to take that and move it into the Eulerian frame so that we can work with the equations and get solutions for velocity field, pressure field, etc. So we are going to use these tools, the Reynolds transport theorem, RTT stands for Reynolds transport theorem, and the Gauss divergence theorem. Okay, so Reynolds transport theorem on the left hand side. Okay, so on the left hand side you will see that d dt of rho v. Now rho v is equal to alpha in the Reynolds transport theorem. So if you take the template of Reynolds transport theorem, wherever you had alpha, replace it by rho v. What you would get is integral of rho v, partial of d dt of rho v plus the surface integral of rho v dotted with v dot n. Rho v comes from alpha, equivalent to alpha, that is multiplied by v dot n. V dot n takes care of the normal movement of the surface, normal component on the velocity on the surface, dA. So this is the entire left-hand side that comes from the Reynolds transport theorem. On the right-hand side, we have a volume integral as it is, so we will keep it. That is the gravitational force. But the surface forces, we are going to convert that into volume force using the Gauss divergence theorem. Okay, so that becomes del dot T over dV, over the volume. Our goal is to get all the terms in terms of the volume integral so that we can combine them. Same idea that we used with mass balance equation. Okay. Now, in going on the left hand side, in using the Reynolds transport theorem, we ended up arriving at the surface integral. So I need to convert that surface integral into a volume integral one more time. And I do that again by using the divergence theorem on the left hand side. So now I am dealing with this term, which becomes this term. That is rho Vv dotted on n. Rho Vv dotted on n is written as del dot rho Vv over the volume. That's over the surface, that's over the volume. That's the volume. Okay, and then I move the quantity from the right hand side to the left hand side. Okay, so these things have come from the right hand side to the left hand side. So that is equal to 0. Now every term in this step is in terms of the volume integral. So I can collect them all together and write it in terms of Vm times V rho V dt plus del dot rho Vv minus rho g minus del dot t integrated over the volume equal to 0. We use the same argument as before. Since this material volume is arbitrary, the only way I can make that integral equal to 0 for any volume is if I make the integrand, that is this quantity, in square brackets equal to 0. And that gives me what is called the stress equation of motion. Nothing but application of Newton's law of motion, but including only two forces, gravity and a surface force, which is as yet undefined. We understand the origin. It's basically shear and pressure. It's molecular in origin, so these are very short range forces. Okay, so that is one form of the equation of motion, and it is not the final form, because we will get into trouble when we count the number of equations and number of unknowns. So we will see how to close the system. Any questions on that page? Or are there any steps that are not clear you want me to revisit? It's straightforward application of Reynolds transport theorem and Gauss divergence theorem to make the statement in a material frame and then move it into an Eulerian frame. Make the statement in a Lagrangian frame and move it into an Eulerian frame. This is a vector equation. From the beginning, when we started in this place, this is a vector equation. Any force balance equation must be a vector equation, right? When I write F equals ma, acceleration has direction, force has direction. So that is a vector equation. So there are actually three components in this equation that is hidden. This is why it is important for you to learn how to expand these vector quantities in various coordinates. In developing this, if you notice, we never said it is applicable to Cartesian frame or cylindrical frame. That's one beauty of taking this material volume approach, because it is independent of particular reference frame that we use. It's applicable for all reference frames, cylindrical, spherical, Cartesian. But we need to be able to expand the divergence that appears here, the divergence that appears here, in those specific coordinates. And that's why we reviewed what are curvilinear coordinates. Okay, so it is independent of the coordinate system, as I said, and it's a vector equation. So there are three components in there. It's valid for all coordinate systems. Left hand side can be simplified further. What do I mean by that? If you look at, let me take this term and compare this to this. What have I done? Chain rule. See, you're getting that idea now, right? Basically the same few tricks, you're going to repeatedly apply that. So apply the chain rule to pull the rho out first and then pull the v out, you get that. Then look at this term. What have I done there? In chain rule. It is basically chain rule. Okay. But if I give you a piece of paper now and then say, show me that, how many of you feel you can do it? Take me from this step to this step. Nobody can do that? Do you see the pattern there? You see the pattern. Okay. How would you get started if you have to do that? Expand it in index notation and work through it. Maybe let's do that, because I want you to get a feel for what are the few tricks that are repeatedly applied. One of them is the index notation. So if I take, let me just go to the other page, del dot rho v, okay, del dot rho v. I want to show that this is the same as rho v dot del v. Plus v dot del rho v. Right? V del dot rho v. V, I think I made a mistake there. That's what we want to show. How do we show this? We write this in index notation. Now, what is V times V? This expression. what would you call it? Dyadic product, Vi, Vj, rho. So what should this index be? There is a dot product, right? It should be xi. Okay? That's how you would convert that into index notation. Now, do apply the chain rule. Okay? Because rho, Vi, Vj all can depend on x. Okay? So if you do that, then you will get rho Vi, Vj, Vxi plus Vj, Vdxi, rho Vi. Written in this form, it's fairly easy to see, right? Is that clear? Okay. So all we are doing is we are grouping it into two groups, rho Vi together, that appears everywhere, and then Vj by itself. Okay, and apply chain rule on those two groups. And then what you do is look at going back to index notation. So if I go back to index notation, I have Vi dxi. And ddxi is going to be del, and Vj is going to be V. But where would I put the dot? Between the first and the del operator, because I repeats there. Okay? And about the second one, I have a V there, I have a del there, and then I have a rho V. Where should I put the dot now? In the second one, because Vi repeats there. Okay? And that's what you get. So it's really just one simple step. You do an expansion, do the chain rule, and then go back to index notation, Gibbs notation. Any questions on that? So you should feel kind of confident in boldly approaching it, at least. Okay, and once you start writing it down, the steps will follow. Okay, that's what we have done to the left-hand side of that equation. Okay, and then what I'm going to do is I'm going to combine the terms that have V in it. So this term multiplied by d rho dt, and then I have V here. I'm going to group them together. Why? Can you see? If I pull them together, then I will have V times d rho dt. I think you should be able to see both of them at the same time. You see both of them at the same time. So, and then del dot rho V. So what is this entire term now? Continuity equation. So that again is equal to 0 by continuity equation. Okay, so you can simplify the left-hand side of that equation a bit more by expanding like this. So whatever is left, of course, you treat them together. So there is rho times dv dt plus v dot del v. Okay, so I'm taking the rho out from both of them as a common factor. Okay, and that can be written in terms of a substantial derivative dv ddt of v. Okay, so the stress equation of motion then simplifies to the following form. That is still the statement of Newton's law for fluids. Now, would that equation be valid for any material? What are the assumptions we have placed on that? So far, only two assumptions: that there is a body force, gravity, and a surface force, T, stress tensor. Okay, no other assumptions has been placed on that. So it should be valid for any fluid, Newtonian or non-Newtonian. That will come when we make a specification for T. That is what is called a constitutive equation. So we need the equation that represents the stress tensor in terms of the velocity gradients. So there are many models. These are empirical models. Those capture the molecular interaction, which is the origin of this stresses, shear stresses or a pressure. They all have their origin in molecular interaction, and because we are not looking at molecular level, we need to come up with empirical or experimental observations on how to relate the stress tensor to the velocity gradients. Now, Hooke's law is an example for solid mechanics, okay, where the stress is related to the strain that you apply. Now, there's one thing that says stress always acts perpendicular to a surface. This is called an inviscid fluid, and we will see that later on. Potential flows. They don't have any viscosity. Of course, no fluid exists like that. But certain fluids, like air, for example, has very low viscosity. So by neglecting viscosity, you'll be able to do a reasonably good job of predicting the pressure profile, for example, on aerofoils. So in aerodynamics, you can use that to predict the lift force with pretty good accuracy without worrying about viscous effects. So it's possible to say that T is simply the pressure. Okay, that's one model. The real model that we are going to use is what is called the Newtonian model, which says that the stress is a linear function of the rate of strain. We need to develop this linear relationship between the stress and the rate of strain. Okay. So the way we do that is take this total stress T and write it as a combination of two parts. One is the pressure, which always acts normal to the surface. The other one is the shear, which always acts tangential to it, even though we know now that there is a normal component also. Okay, so del dot tau. So this is the first splitting of the total stress into normal and shear component. Then we need to figure out, okay, this is the definition for T. What is del dot T? Because that's what we need in the momentum equation. We need to figure out del dot T. Well, we'll make the substitution for T and replace it by minus IP plus tau. Now the del operator is a linear operator, so you can distribute it among two terms. So del dot IP plus del dot tau. Now what is del dot I? I is the identity matrix. So in index notation, I would be the same as delta Ij. Okay, this is the Gibbs notation and that is the index notation. So whenever you multiply something with identity matrix, what happens? Nothing changes. It's the same matrix. So in this case, I dot del will still be the del operator, but its meaning is it's a gradient operator, gradient operating on a scalar field, which is the pressure. Whereas in the second case, it is the divergence operating on the stress, shear stress components, tau. Okay, so you make that substitution, and beautifully what you will see is one by one all the terms pop out in the Navier-Stokes equation, in the equation governing the fluid motion. So originally we had only, oh, this is an error. This should be just minus. Okay, rho g minus gradient of P plus del dot tau. So these are the equations that we have at this stage. This is a minus sign. Okay, but how many variables do we have? If you count the number of variables and number of equations, we have a problem. We are going to treat density as a property. It's given. It's a number. It's a constant. Okay, but we have V1, V2, V3, and P, the three velocity components and pressures, okay, that appear in this equation. So velocity vector V actually contains three unknowns, V1, V2, V3. And the shear stress tensor tau contains tau 11, tau 12, tau 13, tau 21, etc. Okay, it turns out, and we will show pretty soon, that the shear stress happens to be symmetric. If it is symmetric, how many unknowns will there be in that matrix? What does symmetric mean? Tau 12 is the same as tau 21, right? So there must be 6 independent variables in the shear stress tensor. 3 on the diagonal and 3 on the lower side, but the upper side is the same as the lower side. Okay, so we will have 6 components from the shear stress, 3 components of the velocity and pressure. So a total of 10 variables we have in those 4 equations. How do we have 4 equations? This is one equation, and there are 3 equations in here because that's a vector equation. So we have 4 equations and we have 10 unknowns, and that problem is called a closure problem, meaning the system is not closed. We don't have enough equations and variables matching it so that we can solve the system. Okay, we have more unknowns than we have equations. So we need to come up with 6 additional equations, and those are obtained empirically. Okay, empirical meaning I do experiments, I measure, and I relate. This is the experiment that we talked about when I plot shear stress component with the velocity gradient dv1 dx2. I get a linear relationship, I put an equation to it, I have an extra equation. But in the general case, what happens is I have 6 equations in here in the shear stress. So they are related to 6 gradients. In fact, I can form 9 gradients because I have 3 velocities and 3 directions. If I take all possible permutations, combinations, I end up with 9 velocity gradients. But that also turns out to be symmetric, or we make it symmetric so that this is the most general linear relationship that we can write between the shear stress and the rate of strain or the velocity gradients. So D is called the rate of strain tensor, and it is defined according to this. This contains all the partial derivatives of the velocities with respect to position. So in index notation, this is how you would write for the rate of strain tensor. Okay. Now, there is a fairly big theory in arriving at this particular form for the linear relationship, because if you think about it, we have 6 stress components and we have 6 velocity gradients. Okay? So when you write the most general equation, you can write 6 equations and each one will have 6 unknowns, total of 36 unknowns in the most general linear relationship that you can write between tau and d. But we know that these models should be independent of the coordinate system that we use to measure. Okay? So using a series of transformations, and this is done very nicely in the book by Whittaker. I think I probably have given you the reference somewhere. Okay, yeah, C. Whittaker for development of this expression. So he shows that there are only 2 independent parameters, and those are called viscosity, shear viscosity, and bulk viscosity. These are properties of the material. So if you measure them in one experiment, you can use that in any other situation. If I measure it for air, for example, in a laboratory, I can use it for pumping airflow in ducts or aerodynamics, whatever it is. It's a property, it doesn't change. Only when I change the fluid, the property will change. And another interesting thing to notice is this has del dot V. For incompressible flow, we know that del dot V is equal to 0. The continuity equation simplifies it. If you say fluid is incompressible, meaning density is constant. Okay? So for incompressible flow, that will be equal to 0, and the relationship simply reduces to that. The tau equals 2 mu times d. And once again, you substitute for del dot tau, and you will get del plus del v transpose. And that would simplify. I've shown that in index notation when you expand that. Okay, that is, how do you take this and simplify it? So first do it in index notation. Carry out the derivative operator d dxi dj dxi plus d dxt dxi. This again will be 0 because of the continuity equation. Okay, and this will simplify to mu times del square v. That is, this term is the same as del dot tau for incompressible fluid that appeared in the Navier-Stokes equation. So when you make that substitution for del dot tau, these are the final form of the equations of motion. These are called the Navier-Stokes equation. Navier-Stokes equation. Okay, and there are exactly 4 equations in 4 unknowns. The 4 unknowns are v1, v2, v3, and p. The 4 equations are the continuity and the 3 momentum equation. Stress has been related to the velocity gradients, has been gotten rid of, eliminated from the stress equation of motion. Okay, and the entire secret of how fluids flow, Newtonian fluids flow, is hidden in that equation. There is a $1 million challenge for anybody who can solve that equation. We still don't know what the solutions are in the most general case. Okay, why? Because these are complex partial differential equations. There are 4 partial differential equations that are coupled. Okay, and the most important thing is that this term has a product of the unknown. V is the unknown, velocity is the unknown, right? So whenever we have V dotted with del V, it's a product of 2 unknowns. So it's a nonlinear term. This term is called a nonlinear inertial term. It captures the inertia in the fluid. Okay? And this would be called the viscous term because it is capturing the viscous effects, viscosity effects. And of course, this is gravity. And that is pressure. Okay, so and the first one is the acceleration, temporal acceleration. If you pump a fluid from zero, all of a sudden start moving it, there is acceleration in there. That acceleration must occur by externally applied forces. It could be a pump that applies a pressure gradient, it could be gravity when the water falls, for example. Okay, so you can think of the right hand side as the forcing term that acts as forcing on the fluid to move the fluid, and then the entire velocity field, pressure field are governed by these two sets of equations. Most of our course is going to be about solving these equations coupled with heat transfer and mass transfer. Okay, because it is a transport phenomena course, we will learn how to solve this and then how it impacts heat transfer mechanism and mass transfer mechanism. Any questions? You need to go through this section carefully. Okay, I've kind of laid out the logic behind it, but you are not writing it down, and it's not a bad idea to write these things once so that it registers in your mind. Okay. Now, under static condition, we started off with this course with this equation. We developed this equation, del P equals minus rho G. Okay. Do we get that limit? If I take this and say the velocity is zero everywhere in the Navier-Stokes equation, because velocity zero means this is automatically satisfied, and the left hand side will drop out, this term will drop out, and you will have basically a balance between gravity rho G and gradient of P. There's a sign problem that depends on the coordinate orientation that we set up. Okay, so those two are the fundamental set of equations, and it reduces to the limit when there is no flow, to the hydrostatic limit. Now we should next develop the energy balance equation, then we can start solving. The rest of the course is going to be about solving these equations under various scenarios. Limited conditions, as I said, there is no known general solution to that particular set of equations. Now, we said that the stress tensor is symmetric. Okay, why is it symmetric? Under what conditions would it be symmetric? Would it be symmetric for all fluids? These are all legitimate questions. Good section from this one. I think your book also has that. But Panton and Whittaker discuss this very nicely. There's only a brief mention of it in Burstable and Lightfoot. Kundu has a much bigger exposition on this. I've taken this material from Whittaker. When we say that the stress tensor is symmetric, that is an assumption that we place. Okay, not all fluids may obey that again, because the stress tensor itself captures what happens at the molecular level. So if I have a molecule that is highly polar, that has a positive and negative charges, and if I apply an external electrical field, for example, it can resist that. It can develop a torque and start spinning, for example. Under those conditions, I cannot assume that the stress tensor would be symmetric. So it is true only for simple nonpolar material. Newtonian fluids like air and water are not charged, so we are okay with that assumption. But can we show, under those assumptions, can we show that the stress tensor should be symmetric? And the logic, the argument goes like this. I'm going to go through it fairly quickly to just show you the ideas involved in that. Because one of the questions that we can ask is, okay, I have written down the linear momentum balance equation. What happens to the angular momentum balance equation? Certainly one can write an angular momentum balance equation too for the fluid. Okay, but that result is embedded in this particular demonstration that the stress tensor is symmetric. So we're going to start under equilibrium condition. Okay, so remember the basic equation that we have is that the rate of change of this momentum rho v dv equals some of the external forces. Okay, but if the external forces are under equilibrium, then there is no acceleration. Okay, so I'm going to set this equal to 0, and so this is nothing but the equation that I started off with. So instead of ma equals sum of external forces, I have 0 equals sum of external forces. It's like a static condition, if you like. Okay, and that is the force balance. So I'm examining now the torques, asking the question, can the molecule sustain a torque? You all know what a torque is, right? Basically, if I have a force that is acting at a distance where r is the radius to the shortest distance to that force, the torque would be the force crossed with that radial arm. Okay, that would be the mathematical definition of a torque. A physical explanation would be, if I want to, if I want to move this, for example, from one position to another position, I apply a torque. I apply a force at a certain radial arm from that pivot. So I'm applying a torque. Okay? And that's what that expression calculates, R cross F. That torque will be said to be acting on an axis perpendicular to that. So there's a torque about an axis that's perpendicular to that pivot. Okay? So the cross product defines that automatically. What is the direction of the cross product between two vectors? It's perpendicular to both the vectors. Okay? So R cross F will give me the torque. So since I have already the linear momentum equation, all I have to do is cross it, take a cross product with the position vector. So x is the position vector. So x is the distance from an origin to that particular point where that force is applied. The two forces are the volume force and the surface force. So this is the angular momentum balance equation without the acceleration term. Any questions on that? That's translating a concept into an equation. You need to understand what a torque is, how it is defined, and then apply that to the particular situation where there are these two forces. The next thing is a good exercise for you. Okay, it's basically writing it in index notation to simplify it further. Okay, so the first thing I'm going to do is write x cross g. Okay, x cross g. Rho is a scalar, it's a number. Okay, so the vector is actually x and g. So it's going to be eijk xi gj. K is the free index in here. Okay, k is free. So for each k, I will get one component. So angular momentum balance also has three components. Okay, and there are three equations, and each k will give me one component. And then here I will once again have eijk xi, and then what do I do here? N dot t. T is a stress tensor, right? So it has two indices. So when I apply this cross product between x and the resultant of this product, the index for the resultant of that product should be the second index in the epsilon expansion. So if you look carefully, the first one is I, the second one should be j, okay, and k still is the free index, but I have a dot product between these, and that dot product is captured by np multiplied by tpj. So the summation over p is implied. Are you comfortable with that index notation? Okay, so once I go into the index notation, I can then do the chain rule expansion and in fact apply, in this case, the what did I do? Both are under volume integral. Well, I guess I did go from here to here. I also used something else. What did I do? So this one is x cross n dot t. Okay, so in going from this step to this step, I've deliberately left a step there. I want to see whether you can catch that. How did I go from this step to this step? Oh, sorry, from this step to this step. Here it's just index notation, which is what I explained. Okay, and from here to this, I've used one of the theorems. What theorem would that be? Gauss divergence theorem, because I've gone from an area integral to a volume integral. So I have n that disappears, but instead of that, I get d dxp. They carry the same subscript p. Okay, so d dxp operating on eijk xi tpj. So in here I have used Gauss divergence theorem. Now both are under volume integral. I can collect the terms, okay, and I can pull out eijk because that's common in every term. And then I have basically xi rho gj, and then I have d dxi xi tpj, which is that part. Okay, inside parentheses, both multiplied by eijk. Okay, and then I do chain rule. Okay, I do chain rule on what? On this quantity, because I have a product of x and t. So I take x out, then d dxj tp, and then I take tp out, d dxp of xi. Am I going fast? You guys are okay? Now, what is this term d xi d xp? What would that be when you do an expansion? That would be a dyadic product, right? So I and p can take all 9 possible values. So you will have something like dx1 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 dx2 dx1 dx3, etc., right? But dx1 dx2 is what? x1 does not depend on x2. These are independent coordinates, right? So these must be equal to 0, and that's why this entire thing becomes the Kronecker delta pi. Okay, and the remaining terms I've combined here. This one, xi, I took that as a common factor, and this is nothing but the linear momentum equation. So that is equal to 0, because that's what I started off with. Okay, rho g, and then of course if you apply the Gauss divergence theorem, you will get del dot t. Okay, so that is equal to 0 by the linear momentum equation. So that is equal to 0. So all I have is integral of epsilon ijk t tij dv equal to 0. Because when I contract this dpj delta pi, what would that be? Only when p is equal to I, I'll get a non-zero term. So I can replace this entire thing by tij, because p is equal to I. Okay, so tij. So that is eventually what you end up with as a consequence of the angular momentum balance equation applied under local static condition. Now you need to show that for each component that equal to 0 implies that T23 equals T32. So I've just shown that, for example, if you take k equal to 1, and then expand this. This expansion actually has ij repeating. K is the only free index. There are 3 equations in there. So if you put k equal to 1, then ij can take a value of 2, 3, or 2. Okay? So there will be only 2 non-zero terms there. And of course, you need to look at the permutations that will fix the sign to be minus n depending on each class. That is equal to 0, that means T32 equals T23. So this is a demonstration that the stress tensor is symmetric under those conditions where we are not allowing for any molecular level stress couples to be present for simple molecules. So this is important in the sense it takes you through this index notation. It's a good exercise for index notation. So in an exam, I might throw in a question like this: show that the stress tensor is symmetric. You should be able to go through this development. Okay.
What's the reason why rho gi does
Why does it go to 0? Because that term, this is the same idea like we have when we see a continuity equation, we said the continuity equation is equal to 0, right? So in the same way, these terms are coming from this equation. Rho g dv plus n dot t, right? So when I apply the Gauss divergence theorem to this, I will write this as integral of rho g plus del dot t dv equal to 0. And so rho g plus del dot t is what I have there. I've combined. So that must be equal to 0 by the linear momentum equation. Okay?
I have a question.
Yeah.
That Tij, how can
This one? Oh, this one?
Yes, yes.
Okay, so what I'm saying here is it is Tpj delta Pi. You first understand how delta comes there, right? These partial derivatives will give you delta. Okay, now this is the same as if you do the expansion on P, there's a summation on P implied here, right? So you must put in P equal to 1, and then P equal to 2 and P equal to 3, and then add them up for each value of I and j. Okay, when you do that, you will find that only when P is equal to I, it will multiply by 1. When P is not equal to I, it's going to be 0. So in this term, the only time it will get a non-zero value is when P is equal to I. Okay, and that's why we say that this is the same as Ij. Now, if that kind of argument doesn't convince you, then just go do the expansion. Okay, write it out in detail, and you will find that only time when it is not 0 is when P is equal to j. This is called contraction. You can always do that trick whenever you have a multiplication by delta. For example, if I give you Vi delta Ij, what is this? This is the same as Vj. Okay, because only when I is equal to j, you're going to get a non-zero value. So you can simply contract that into a single expression. Okay, the same idea. Any other questions? Okay. Was there any question? I didn't miss it. Okay. This is the most important set of equations you should know. These are the expanded form of the equations I have presented. For example, this equation we derived, that is a continuity equation in a compact form. But in Bird-Stevens and Lightfoot, in any book in fluid mechanics, you'll find an appendix where they give you the expanded form. Okay? So you don't have to expand it in an exam. In an exam, you should have these ready. So this is essentially the continuity equation in Cartesian frame xyz. So you can clearly see del dot rho v, that means d dx of rho vx, d dy of rho vy, d dz of rho vz. That's a dot product. So in a Cartesian frame, v is vx, vy, vz, coordinates are x, y, z. Okay? In cylindrical frame, that doesn't look anything that I could easily write down. How did I get all those 1 over r terms? Those are the metric coefficients. So if I'm expanding this del dot rho v in any coordinate system other than the Cartesian frame, the first thing I need to do is get the metric coefficients in that coordinate system. Then look for the expansion of the divergence of a vector field in that coordinate system. That will have h1, h2, h3. And these are given in the book by Happel and Brenner. Also, Bird-Stevens and Lightfoot, the current version has that. The earlier version did not. Okay. So these are the expanded versions of the continuity equation, cylindrical coordinate in spherical coordinate. You will be doing problems with these. Okay. So most of the problems we are going to do would be just you're studying a problem in spherical coordinates. Let's go and take a look at these equations, write them down, start simplifying them. Okay. And similarly, the stress equation of motion, this is what we developed. Minus gradient of P plus rho G. Now he has a minus here, minus del dot tau. That it depends on the sign convention, whether the stress acting on a surface is positive or negative, compressive or tensile. Okay. But eventually he will have tau equals minus. So in every term that you have tau, you will have a minus sign there. But these are the components in Cartesian frame of the momentum equation. There are 3 momentum equations, Vx, Vy, Vz. Okay? And these are the equations that we want to solve. You can see that clearly multiplication of Vy, Vy, these are the nonlinear terms, the inertial terms. All these terms are called the inertial terms. Okay? And these are the viscous terms. And of course you have the gravitational term here. Okay, so you should be able to use these expanded in any coordinate system. Okay, I also pulled down the material for the Navier-Stokes equation, which is getting rid of the stress in terms of the velocity components. So these are now in terms of the velocity components directly for the viscous stress. Okay. Once again, the left hand side is the inertial term, the right hand side is the viscous, pressure, and gravity terms. So see Appendix B for other coordinates. Okay. Any questions on that? Just for quick reference, you will be. We will discuss when you get close to the midterm exam whether you want an open book exam or a closed book exam. If it's a closed book exam, these formula sheets will be given to you. Okay, so next we can get ready, started with the energy balance equation. Okay, this is our linear momentum balance equation that we developed just now, and in index notation I can write it in this form. Okay, d dxi of tji. Now remember, T is a symmetric tensor, so Tij is equal to Tji. Now, and there is an important concept. How do I get energy balance equation from a mass balance equation? Can I get a momentum balance equation? Can I get an energy balance equation from a momentum balance equation? Here I say that take a dot product of the velocity to get the mechanical energy equation. What is energy? Let's go back and ask that question. What is work and energy? They are kind of related, right? Second law, we're doing thermodynamics now. Well, most of you should have seen the energy balance equation there, right? Internal energy change equals Q minus W. We're going to use that pretty soon. That's first law, right? We're going to see that energy conservation. Okay, but mechanical energy. I'm going to talk about mechanical energy equation. So if I have, what is work? Work is force times rate of work is force times velocity. Work itself is 4 times distance. Okay, so if you have so many newtons and you move it through 1 meter, Newton meter is joules. Okay, that's your energy that you would spend in moving a particular object with a certain force from one place to another place. And so velocity times, the velocity times a force dot product, because energy is a scalar quantity. Okay, so V dot F should be equal to rate of work. That fundamental idea is what we are going to use to take the momentum equation that we have, which is a force balance, and dot it, dot product with the velocity. V dot F in general is work. So if I take this equation and dot it every term with the velocity vector, I should get a scalar, because this equation is a vector equation. Okay, so I'm dotting it with V dot, that should give me a scalar. And so I'll take the first term, that is a substantial derivative of V, and I dot it with V. So what I've done here is I've written it in the form of 1/2 V dot V. I'm dotting V with respect to V. Okay, so this is the same, these two terms are identical after I dot it with V. Why is that? What do I have? I actually have rho V dot d dt of V. That is the left hand side. Okay, rho is already there, I'm dotting it with V. Okay, so I'm saying that I can write this in this form also. Rho still remains outside, but V goes inside the derivative. Okay, and when I do that, I have to put a 1/2. Why? Basically what I will have is d dt of Vi squared. Right, V dot I is Vi squared. So which will give me, when I take the derivative, 2Vi dvi dt. So when I take the derivative from this one, I'm going to get 2Vi dvi dt. So if I write it as simply V squared, that is V dot V, I will have an extra 2. To compensate for that, I put the 1/2. So that these two are exactly the same. The left hand side becomes d dt of 1/2 V dot V. On the right hand side, I will have V dot G as it is. I'm not doing anything with that. And then I will have V dot del dot T as it is. I'm not doing anything with that. But I'm reinterpreting this term. D dt is the total derivative, which is equal to the partial derivative plus rho V dot del. Now I called E as my 1/2 V dot V. What is the meaning, physical meaning that I can give to V dot V, 1/2. Kinetic energy. Do you remember from undergraduate fluid mechanics Bernoulli's equation? No? We will derive the Bernoulli equation soon, but you would have seen that. What does Bernoulli equation tell conceptually? You don't have to remember the equation, but you must have heard of the equation. That's the one equation that you use most in undergraduate fluids course. If you come out of a fluids course, one thing that you should remember is Bernoulli equation, if nothing else. Okay? That is a mechanical energy balance equation. It simply says sum of kinetic energy plus potential energy plus pressure energy is a constant along a streamline. Okay? So if you take 2 points in a pipeline, some of these energies, potential, kinetic, and pressure, should be the same, except for losses in the pipe. Okay? So it is derived for frictionless fluids, fluids that don't have viscosity. The Bernoulli equation is derived for those. So the meaning, the physical meaning that we can give to this half V dot V is that it is kinetic energy. So I'm representing this E as the kinetic energy. Okay, so that is called a mechanical energy balance equation. So in fact, you can see a relationship between this and Bernoulli equation. Bernoulli equation is one step away from this. If I drop the shear stress, because there is no viscosity in the Bernoulli equation, there is no friction in the Bernoulli equation, but there is pressure. So I should replace T by P, and then I will get the 3 terms: the gravity, the pressure, and the kinetic energy. Okay. So a mechanical, the short lesson is that the mechanical energy balance is obtained from momentum balance by dotting it V, and then reinterpreting that 1/2 V dot V as the kinetic energy. Okay. Now multiplying the kinetic energy by the continuity equation is still 0. Continuity equation says d rho dt plus del dot rho v equal to 0. Multiplied by E, it's still 0. Okay. And the reason I'm doing this mathematical manipulation is I can add that to the left hand side. Okay. So this is my original equation. To the left hand side I am adding this extra term E d rho dt plus del rho v, but this by definition is a continuity equation. This is equal to 0. It's like adding 0 to the definition. The reason I want to do that is I want to again apply chain to combine them. For example, d rho e dt is the same as rho times d dt plus e times d rho dt. So this will split into the 2 parts. Okay, so this is the same as a combination of these 2 terms. And similarly, this is a combination of these 2 terms. Okay, so I'm able to compactly write the left hand side as energy flux, kinetic energy flux. Okay, so the physical meaning for this one is that this is the, I guess I've written it down already, kinetic energy flux. So the material derivative of the kinetic energy flux is influenced by any work done by gravity or any work done by shear forces. Any questions on that? So that is a mechanical energy balance equation. We'll come back. We need to, ultimately what we are after is a thermal energy balance equation. So we need to write a total energy balance equation, which is first law of thermodynamics, and then we'll look at the mechanical balances. This simply tells you that there is a balance between mechanical forms of energy, and from that we need to look at how to predict temperatures. From this, by solving this, we can say something about velocities and kinetic energy, but we cannot say anything about temperature yet. That's what we are going after. Okay, so we'll come back to this equation, but let's go to the thermodynamics, the first law of thermodynamics. Okay, so the total energy balance equation, in statement it will be simply that the rate of internal energy change is equal to the heat added to the system, the work done by the system. That is du equals dq minus dw. What is internal energy? Absolute silence. In thermodynamics, you haven't seen that yet. These are concepts. If I ask you what is force, what is gravity, you will wonder what is gravity, right? We know that it exists. If we propose that idea of a gravity, then we can predict the consequences of planetary motion or whatever. Okay? But the concept of a gravity itself, the gravitational force, would be difficult to explain if somebody comes and asks you, what is electromagnetic force? What is a gravitational force? What is a weak nuclear force? Okay? These are concepts that we propose. And from that concept, we build these structures that help us try to predict what the behavior will be. But you cannot really explain what is the origin of gravity. It just exists. What is the origin of electromagnetic force? Right? So in that sense, the internal energy represents conceptually an energy state. It is ultimately due to the molecular nature of the interaction. Okay? So if I say some material has high internal energy, you can translate that into saying it has high temperature. So if I add a lot of heat to it, temperature goes up, but its internal energy is at a higher state. But it's a macroscopic view of what happens at the microscopic level due to the molecular interactions. Okay? So if I add energy, the molecules are actually, in a solid, they are vibrating more probably. In a gas, they are bombarding against each other more. So their state of energy state is at a higher level. Okay? So the internal energy is in that sense a concept, but the equation that the symbol that we introduce and the equations that relate those symbols allow us to calculate any one of those quantities if I know the other quantities. That's the idea of any modeling. The modeling purpose of a modeling is you have a concept and you describe the concept in mathematical language, and then that symbol, that equation will have many symbols in it. If you can write additional equations so that we have number of symbols matching the number of equations, we can solve them. If not, you need to provide some of those symbols, you can calculate the other symbols. In the process, we are saying that energy is conserved, mass is conserved, momentum is conserved. These are the fundamental concepts that we apply. So in this case, the internal energy, the rate of internal energy change is equal to the heat added to the system and work done by the system. And there is a convention here too. Okay? So heat added to the system is treated as positive and work done by the system is treated as positive. Okay? So you're taking work out of the system, so the internal energy will go down. If dW is positive, for example, there is no dQ, no heat, but you're taking work out of the system. dW is positive. Then, because you have a minus sign there, the internal energy will go down because you have extracted something out of it. Okay? Keep dW 0 and see what would happen to internal energy as you take heat out. Okay? Or as you add heat in. It says heat added to the system is positive. So if I add heat, it means positive, the internal energy goes up. If I take heat out, that dQ will become negative. So the internal energy goes down. Okay? This is how at least I remember the sign convention. Okay? So the rate of internal plus kinetic energy, this is for a non-flowing system, a closed system, okay, which has only internal energy. But if I have an open system, I have material coming in and going out, then I have internal energy plus kinetic energy. This is for a flowing fluid. So the rate of change, the sum of the rate of change of these two must be equal to heat added to the system, work done by the system. That's a conceptual statement of conservation of energy, which includes all forms of energy, including work, including heat, and other forms of energy. Okay? Once again, we are going to consider the material volume and calculate the total energy in the material volume. So U is the internal energy, 1/2 T is the kinetic energy. We need to add those two and then multiply it by rho. That gives you these are, what would be the units for energy, internal energy? So many joules per kilogram or kilomole. Okay? So you're multiplying it by kilogram per unit volume and multiplying it again by the volume. So this whole thing is the total energy, okay, in terms of joules. The units of that would be just joules. And that is the energy content in that material volume that we are looking at. And so the rate of change, that's what gives you the ddt. So joules per second. The rate of change of the total energy, we have figured out symbolically what the left-hand side should be. And that should equal heat added to the system and work done by the system. Now again, we need to make certain assumptions, or we need to find an expression to capture those. So we are going to assume that there is no radiation. If you include radiation, you need a model to see how much of radiation is added. You need an expression for that. And so we're going to have really convective flux. Remember, this is a material volume, so no energy can go into by flowing and out. So the convective part is already captured in the total derivative, material derivative. Okay, so all we can have is energy still can be transferred by conduction without material getting into it. That is, a molecule that is staying outside is vibrating and making the molecule inside vibrate. So that's a conduction mechanism. There is no material transfer. So that we are going to represent by the flux Q, so many joules per meter square second. It's a flux per unit area. Okay, second. Now this is the same type of constitutive model that we use for shear stress. What is shear stress? After all, a molecule that is shearing this place is causing the fluid inside to move by molecular interaction across the boundary. Okay, so in the same way that there is a thermal interaction, there is a molecule that is vibrating here is causing the next molecule to vibrate, transferring its energy that way. Okay, and these are all molecular processes, so we need an empirical model to capture that. And the empirical model here is, of course, Q equals minus K gradient of T. In the velocity case, in the shear stress case, shear stress was related to velocity gradient. And here the heat flux is related to the temperature gradient. That's an empirical relationship that defines a new property called thermal conductivity, just like we introduced viscosity with the other one. This is where the similarity is between the three transport processes, fluid mechanics, heat transfer, and mass transfer. Fundamentally, they are very analogous processes. So this is the symbol that we introduced to account for heat added to the system, and only way heat can be added is by conduction, because we have neglected radiation. Okay, and I have to evaluate that over the entire surface because it's a surface process. It's a surface phenomenon. Okay, it occurs over the entire surface of that material volume. Now here I have put some symbols. How are we doing for time? Okay, so N is always the outward normal. I put a symbol of minus Q here. I want to explain why I put a minus sign and how it is consistent with what I said there. So it's a convention. You need to be comfortable in understanding and using it consistently. Okay, so Q, suppose, is going in. In this case, Q is coming out. That is, through one surface, heat is being conducted into the material volume, perhaps because the temperature outside is higher than the inside. But in this side, the temperature inside is higher than the outside, so heat is leaving by conduction. So in this case, Q is pointing in the same direction as N. So what would Q dot N be? Positive, right? Q dot N would be positive. The dot product between Q and N would be positive. And that means this number is going to be evaluated as a positive number. Okay? And that means I'm removing heat. So I must actually have a negative sign. That's why I have that negative sign, to fix the assumption that I need that heat added to the system is positive. Okay? So in this case, I am adding heat to the system. Okay, but Q dot N is negative because Q is pointing in one way and N is pointing in the other way. Okay, so the dot product between Q and N would be negative, and that will flip the sign to be a positive one because there is already a negative sign there. Okay, and that would mean that I'm adding heat to the system, and that would be a positive number. Okay, so it's just a matter of sign convention, but you need to understand why the negative sign is there to fix the sign correctly in the first law of thermodynamics. Okay, so N is always defined as the outward normal, but Q could be outward or inward. Yeah, by convention, compressive force is positive. T and N are in the same direction. Okay, then you have tension, and T and N are in the opposite direction. You have compression. Okay, so it's just the same way that Q and N in the opposite direction means that you are adding. Q and N in the same direction means that you are removing heat. Okay, so putting all these together, we have identified each one of those terms. We have identified the term for heat added. We have identified the term for the work done by these two forces, gravity and the stress, the total stress. We dotted with normal. Once again, the same idea as before. Okay? So this is the work done by these two forces, gravitational force and the shear force. So on the right hand side, then we have heat added. Let me take this heat added, which is this term, and which appears here. That's a surface integral. Okay, and on the left hand side we have the total kinetic energy, and the internal energy, which is this term. Okay, we are making substitution into the first law of thermodynamics, and then we have the work done by the system. I guess I should probably pick a different color. Okay, work done by the system, and there are two possible sources of that work by force, external forces. So we obtain that by simply dotting V with that, and those are these two terms: work done by gravity and work done by shear. Can you think of an example of a work done by gravity that is converted into useful work? Any hydroelectric dam, for example. Okay, you have water at a high level and it just flows down by gravity. Okay, and you can tap that energy by putting a turbine at the bottom. Okay, so that kind of work will be captured in here. Work done by shear and pressure, any compressor, any piston, any pump, those will be doing work through these terms. Okay, and of course heat added is captured there. I think we're almost out of time. So once again, it's the same trick. Use divergence theorem, use Reynolds transport theorem, and get it into a form that we can understand and interpret and work with. Okay, well, let's stop there and we'll continue from this point on in the next class. Again, tell me, I keep talking fast. If I keep moving fast, for you to understand, you need to slow me down. Okay? And there is a lot of material in today's lecture, so I would highly recommend that you go through this